name is Marcin Hoffmann and I'm with Institute of Radio Communications, Poznań University of Technology. I'd like to present my paper entitled Federated Learning Based Interference Modeling for Vehicular Dynamic Spectrum Access. Our work is focused on the wireless communications in a so-called platoon-based driving scenario. In a platoon-based driving, vehicles follow each other at short distances of a few meters. There are several significant benefits originating from this approach. First, due to the short inter-car distances, the road capacity can be improved by placing more vehicles on the road. Second, vehicles following each other benefit from better aerodynamics conditions. This further implies fuel savings and reduction of emitted pollution. In most cases, the platoon leader, first vehicle, is responsible for the platoon behavior. Other vehicles not only adjust their speed to the platoon leader but also follow its maneuvers. For example, line change. However, it is not a trivial task, especially when the platoon leader is forced to sudden braking. Research has shown that for the purpose of safe driving while maintaining short inter-vehicle distances, it's not enough to rely on onboard sensors of camera. Additionally, reliable wireless communication must be established between the vehicles within the platoon to exchange information, for example, messages related to speed adjustment. There are several protocols already defined that are aimed at wireless communications between vehicles. These are collectively referred to as vehicle-to-everything, named widely V2X. In general, the idea of V2X communications can be realized either in a centralized way with the use of a cellular technology, or in a distributed fashion by means of dedicated short-range communication. Although there are dedicated frequency bands for both DSRC and CV2X, this may not be sufficient when road traffic is high. Therefore, it seems reasonable to look for alternative frequency bands where intra-platoon communications can be offloaded. Although almost all frequency bands are assigned to some wireless systems, the majority of these spectral resources are underutilized. A platoon can potentially use a frequency band if it is not used at a given time in a given location. This requires detecting the radioactivity of the so-called primary users, who are licensed to transmit in a particular frequency band. If primary users' activity is not detected in this frequency band, this part of the spectrum can be opportunistically used by other systems. However, the frequency availability can vary within location or time. In this work, to deal with potentially complex distributions of interference generated by the primary users, a Gaussian mixture model will be used. Based on the model, a wireless channel capacity can be calculated and the optimal frequency can be obtained. As the Gaussian mixture model of interference varies in space, we propose to store Gaussian mixture model location pairs in the radio environment map. Moreover, we propose a two-layer architecture of radio environment map dedicated for vehicular dynamic spectrum access, consisting of a global and a local radio environment map, respectively. In our approach, platoons can download the estimated Gaussian mixture model from the global RAM to its local RAM and update local RAM during ride based on local spectrum sensing. Later on, the locally updated Gaussian mixture models from potentially many platoons are sent back to the global RAM to be merged into a single model therein. Such an architecture is enabled via federated learning. Let us consider the generic case where platoons offload a portion of their traffic from congested CV2X or DSRC bands to other frequency ranges already occupied by the primary users. The selection of frequency channel consists of several steps, mainly spectrum sensing, interference modeling, and channel quality assessment. The first step is to capture power samples from secondary spectrum channels available at location, XL. We assume that every vehicle in the platoon can be potentially involved in this process. Thus samples can be simultaneously collected from several secondary spectrum channels. In each channel, a batch of m in phase and quadratures received signal samples is collected in total. The secondary spectrum channel can be occupied by many interference sources of different emission powers, diverse radio access technologies. As a result, the interference can follow a non-trivial multimodal distribution. It has been shown that such multimodal distributions can be efficiently modeled with the use of a so-called Gaussian mixture model. The idea behind the Gaussian mixture model is to represent an arbitrary probability density functions, PDF, as a properly weighted sum of several Gaussian mixture distributions probability density functions, as presented in the equation on the left side of the slide. We assess the channel quality in terms of outage probability based on the Shannon capacity of the secondary spectrum channel between the two most distant vehicles in the platoon. The mathematical formula takes into the account simplification for low SNR, as given on the right side. From the perspective of spectrum management and the best channel selection, the radio environment map may be treated as an intelligent database containing location-dependent information about various signal sources, both wanted and of interference type, observed in the wireless communication system. Each location is associated with the dictionary of tuples, channel, and related Gaussian mixture model parameters. From the architectural perspective, we propose a two-layer scheme where global RAM and local RAMs are shown. Global RAM is a part of the network infrastructure belonging, for example, to mobile network operator. It stores the global interference models, distributes them to the local RAMs, for example platoons, and is capable to combine them together in order to update its own global interference model. In turn, the local RAM is deployed and managed, updated at each platoon. Thus, in our case, in the first step, the local RAM will be populated by the data downloaded from the global RAM. Next, these entries will be updated locally every time the platoon captures new samples of interference. Once processed locally, they will be used for updating the global RAM when the link to it is available. The procedure of local RAM update, described together with the procedure of global RAM update, would follow each other in a cyclic manner in order to learn global RAM with interference distributions. This constitutes a federated learning cycle that, according to the principles defined in the literature, can be specified as shown on the slide. This federated learning cycle can be visible also in the proposed two-layer radio environment map architecture in the previous slide. The detailed mathematical description can be found in the full text of the paper. The procedure of secondary spectrum channel selection, which utilizes interference modeling based on radio environment map and federated learning, is summarized in this slide. It can be seen that it is an extension of the state-of-the-art stand-alone interference modeling approach that was presented before. To guarantee the reliability of a model, a dedicated and detailed simulation environment has been built in order to generate interference samples along with the consecutive platoon locations. We consider the three non-overlapping wireless local area network channels having 2.412, 2.437, and 2.462 GHz center frequencies respectively. At the same time, they formulate a set of available secondary spectrum channels, for which we model the interference using the proposed algorithm. We have chosen the ISM band. It is motivated by the fact that there are many devices of potentially various medium access control algorithms and modulations transmitting therein. As a result, non-trivial interference distributions are expected to be observed, which makes the modeling process challenging. We are considering a 1 kilometer long fragment of a road, which is split into 30 equally spaced segments, platoon locations. Moreover, there are in total 11 wireless access points deployed along the considered platoon road. They generate interference over 3 different radio channels that corresponds to orange, purple, and yellow triangles respectively. The considered location can be simultaneously visited by one or more platoons. The simulation parameters are as follows. The number of vehicles in a platoon is 3. Platoon to the last vehicle distance is set to 50 meters. Distance traveled by the platoon is 1 kilometer. There are 30 platoon locations that are visited during simulations. There are 11 access points. Secondary spectrum channels have the following center frequencies: 2.412, 2.437, and 2.462 GHz. Secondary spectrum channel bandwidth is set to 10 MHz. Transmitted power per subcarrier is 3.19 dBm. Desired capacity is 3 megabits per second. Number of subchannels are 64. Number of usable subchannels are 48. The traffic rate parameter is 0.0054 milliseconds to the power of -1. At first stage, we have analyzed an interference distributions on the basis of large batch of capture samples, about 40 million of IQ samples. This reflects a scenario where all data captured by the platoon were reported to REM and the proper Gaussian mixture models were computed. There are representative examples of probability density functions related to interference distributions depicted in the slide. As it can be observed, the distributions are complicated and they are varying over locations and between channels. On the basis of these results, Gaussian mixture models have been created for every secondary spectrum channel in each of the 30 platoon locations. They will serve as baseline models for evaluation of the proposed algorithms. In this scenario, U platoons travel through the set of locations 15 times. This procedure is repeated 50 times in order to average the results. Our focus is to put on the impact of number of platoons on the global REM improvement. The outage probability computed with the global REM and baseline models are compared in terms of root mean square error. In addition, the plot contains a result that refers to the scenario where the interference model is computed independently at each platoon only on the basis of the currently captured samples. It is SAIM. The first observation is that benefits from utilization of historical data in REM and federated learning are significantly compared to the standalone interference modeling. In the case of a single platoon, root mean square error after many REM updates is about 3 times lower than the root mean square error obtained for standalone interference modeling, which is not improving as a result of a lack of memory, like REM. Moreover, in the case of simultaneous global REM update by 7 platoons, a 4.5-fold reduction of the root mean square error can be observed after 15 REM updates, referring to the standalone interference modeling. In this slide, there is an index of channel offering the lowest outage probability in the consecutive platoon locations computed on the basis of the baseline model, the model utilizing REM with local and global REM updates, and standalone interference modeling. It can be seen that channels marked as the best on the basis of interference model from REM cover up with the ones computed using the baseline model in all cases, which is highly expected and proves the correctness of the proposed method. On the other hand, results based on standalone interference modeling correctly indicate the based radio channels only in 24 out of 30 Platoon locations. It means that on the basis of only currently available interference samples, the best secondary spectrum channel can be selected only in 80% of cases. It is important to note that such mistakes can have a significant impact on the quality of wireless communications between vehicles formulating a platoon. This can further imply decreased fuel saves or platoon crash in extreme case. To conclude, we proposed a two-layer architecture of radio environment map together with federated learning and local spectrum sensing can be effectively used to provide platoons with an accurate model of interference. We have shown that Gaussian mixture model accurately models the non-trivial distributions of interference in vehicular dynamic spectrum access scenarios. Through the extensive computer simulation studies, we came to the conclusion that historical data from REM can much improve the accuracy of interference models used by the platoon to predict radio channel occupancy in relation to the state-of-the-art standalone interference modeling approach. Moreover, it has been observed that due to utilizations of federated learning, multiple platoons can contribute to improvement of global REM interference models even more. Thank you for attention. I highly encourage to read whole paper to get more insights into the presented topic and solutions.